Welcome. I'm very pleased to introduce Mr. Rich Barrett and the Fastener Design course. Rich, as you may well know, is a NASA engineer. He has been an engineer for 40 years and with the Lewis Research Center for 34 of those 40 years. He's advised in the materials of fasteners and materials is well sought by industry and by other government agencies besides NASA. His Fastener Design Manual has received widespread acclaim and distribution, and it led to his earning of the Federal Laboratory Consortium Award for Technology Transfer. Other awards that Mr. Barrett has received are the NASA Exceptional Service Medal and the Elder Statesman of Aviation Award. With not much more to say, here is Mr. Rich Barrett. Thank you very much.
Thank you, Mario, for the nice introduction. We will be presenting in this course it will be the most extensive coverages of fastener design that I have done to date, because it will be about 385 pages of presentation. So we will move into it, and as they say in the candy commercial, you're not going anywhere for a while, so relax, and we'll cover everything we can on fasteners. Thank you. So to start out with, I'd like to give you some acknowledgments here of the people that had a hand in this. Will Harkins and Mario Castro. Mario is my boss here at NASA Lewis. Will Harkins from NASA headquarters sponsored this course, funded quite a bit of it. So this will be used by all of the different NASA centers. Harold Casper from Analex Corporation. He wrote some of the sections and found some information for the others, as well as editing the entire course. John Bickford, who is the leading author actually in the fastener field, he is the editor-in-chief of a book which I was contributing author for. It'll be published at the end of the year. I used a lot of John's stuff from his book on fastener design in this course. Bing Blendoff from Clemson University, and he's actually chairman of the Bolting Technology Council, which is a council dedicated to furthering the knowledge on fastener design, has contributed some. And Betsy Dela Cruz, who did all of the typing, retyping, running, and so on to get this thing together, and we just about ran out of time. But that's why we did not give it before, and I say it's approximately a 2-day course. Then Ray Holmick from ADF Corporation edited the entire course and had some very helpful comments. So with that in mind, we'll proceed with the little introductory material. Now, there's a statement everybody knows about bolts and nuts, but do they really know about bolts and nuts? Sometimes we oversimplify things because we think because it's something that a kid took off of a wagon that it's simple for everybody. Joseph Dudley, who is Vice President of Automotive Marketing for Nylock Fastener Corporation, gave these two quotes. 75% of the assembly labor cost of an automobile is spent on fasteners, and 80 to 85% of all automobile recalls are fastener related. Now that gives you an idea about the importance of fasteners in putting things together. And of course, some of you remember on the shuttle recently when they had to cancel a spacewalk because a couple screws came loose and fell out in the gears. They couldn't get the door open. So things do go wrong like that. Here is a summary of the causes for joint failures in NASA's Skylab program. Some of you, say Ron Romanchuk, will remember that. He was here that long back when that happened. And the thing that surprised me in this is the poor design, improper assembly here. 24% poor design, 28% for improper assembly, and yet only 10% for bad parts and the 24% for parts damaged in handling, and the wrong preload, 14%. Now, we have been hearing in the news for the past several years about the counterfeit fasteners and all of that, and so it's gotten quite a bit of publicity, and it should, but it still boils down to the fact that the designer has more to do with it than the manufacturer of the fasteners. Now, here is something from John Bickford's book on a bolted joint, just a spring concept, because actually you don't think of it this way, but the joint material itself is a big heavy spring, and you're compressing it with small springs, which are fasteners, and we even get into joint stiffness and stiffness ratios and so on. Now, here's a summary of the different types of heads on fasteners, just to for your reference. And this is used some in the aerospace field, although it's not that common. But of course, the flat, the socket head over here, and the hex, all of these are very common. The carriage bolt, of course, that one is, I guess, dates back to building wagons when you drilled a hole and you pounded that one in, and the square part under the head there locked it in place while you put the nut on. So, Betsy, that's how you build wagons, in case you ever go into it. Here's one on the internal drive systems, and you can't read it too well on this one, but over on the view graphs, I think you can read them. And a lot of these are common only to the aerospace world, like, for instance, something like this, or something like the tri-wing type here. These are used only by certain manufacturers. The Torx down here is very common in the automotive field. That one, I thought that I'm always looking at conspiracy theories of designers, and I thought that Torx was developed by the automotive people just to make things more difficult on working on your car, but I found out that the reason they used it was that it centers better than the Phillips, which various types of Phillips there, and will not cam out as much, so therefore it will work better in automated assembly. Now, getting into the agenda for this program, see, we have a lot of stuff, and each one of these is a section number in your handout. So we have a lot of stuff here to cover. I won't go over all of these, but I'll point out that at the end we have a do's and don'ts and frequently asked questions sections that will answer some of the various questions that I have been asked from time to time by people. So we'll move on into materials, and this I feel is a very important section because you need to choose the right material to begin with, or you're dead in the water on a design. Now, fasteners can be made from many materials, but most of them that we're familiar with are made out of steel. The hardware store type that are made out of what's called low-carbon steel, then the alloy steel for the grades 5s and 8s that we use around here in the socket head cap screw. Titanium and aluminum bolts have limited usage in the aerospace industry, but on the other hand, aluminum and titanium are used a lot on the aircraft design, particularly since you have aluminum skins on most airplanes, and you want the rivets to be of the same material because of the differential temperature giving you problems on expansion and contraction. So now the alloy steel fasteners, you can get them up to 300 KSI, KSI being 1,000 PSI, so it's 300,000 PSI strength levels. But I'll try to point out to you here that in most cases you really don't want to do that. Okay, now carbon steels are not corrosion resistant, so they usually have to have some kind of a coating to protect them from rusting. And the stainless steels you can get in all varieties of both heat-treatable and non-heat treatable alloys with tensile strengths of 70 KSI to 260, the 70 being the ordinary 300 series stainless that we use here all the time. And the 260, you're talking work-hardened Inconel 718 or A286. And note that the 400 series materials contain only 12% chromium, which will allow them to rust some. So if you're building something that you want it to look pretty, the 400 series stainless would not be advisable. And on some of the subsequent tables, we will show various materials, but just go on to the, in order here, on the selection of materials. You should use common fastener materials, strength levels, and coatings if you can. There's no sense in overkilling on any design because it just costs you money and time usually. Weight savings versus cost must also be evaluated for flight articles, and there you do spend a lot of money to save a little bit of weight. Galvanic and stress corrosion tolerance levels have to be established and checked out. And of course the operating temperatures have to be determined before the material is chosen, both the high and the low, to make sure that the materials are compatible in the entire range. And then the type of loading, static or fatigue loading, is also a factor in the material selection. Now, as far as availability of materials, the carbon steel fastener materials, of course, everybody's familiar with the 1010, 1020 that we use around here, and that is just a iron with carbon in it and a few impurities, and it's up to 0.28 carbon. Now that's, I'll explain this further in another chart, but the carbon content is usually called out in points, and it's actually hundredths of a percent. So this is 0.28 here, it's hundredths of a percent of carbon. And you need, for heat treating, unless you add something like boron to the material, you need about 25 points of carbon really to get it to heat treat properly if you're going to heat treat a fastener. Now the grade 5s and grade 8s are in the 28 to 55 point carbon range so that they're heat treatable. And the 8s, of course, have other alloying elements in them in order that you can bring them up to the strength that you want. And 4037 is one of the common materials for grade 8. Now, here's something I just wanted to point out to you that the Charlie Wilson from the Industrial Fasteners Institute has been trying to get this changed for years, but it's still in there in SAE J429 spec, which is for grade 8 fasteners. There's a footnote there that allows the manufacturer to furnish these in 1045 plain carbon steel if the buyer agrees to it. Well, the only thing is, if the buyer doesn't know he's agreeing to it, he can get one that will not have very good impact resistance. And we had a problem that we were in on one time with the Army on some Abrams tanks, that when they fired the cannon on them, it broke the bolts on the turret because they were made out of 1045 steel. Okay, moving on. Now, the ASTM fasteners are used primarily in the construction industry. So since a lot of you are not familiar with them, and I'm not that familiar with them either, I put in some equivalency here, like the A307's a grade 1 in the SAE that we're familiar with, and 449, 354. And now the A193, they're the B5, 6, 7, 16s, and also the B8 stainless steel. Those are used a lot for the pipe flanges that we design around here. So a lot of you are probably familiar with them. The 320 is an alloy steel for low temperatures, and 325 is a sort of equivalent to a grade 8 in strength, and then the 490 is the highest strength of the construction type fasteners. Now, stainless steel, which is a crest, you'll see that designation for it, corrosion resisting steel. Stainless steel is the same generic terminology, and the superalloy materials. Now, the 300 series that we're familiar with around here, you can get it up to about 80 KSI because it's not a heat treatable material, so the only way that you can get the strength up on it is by work hardening it, and in forming it, that's about the strength that they get starting with annealed material. A286 we use all the time in the aerospace world, up to 160 KSI. It is a very common aerospace material, and you can get it in metric by special order in A286. The 400 series is available in limited strengths up to 125 KSI, and it's also available in metric, which I will show you further on. Now, the super alloys here, these are the ones that you guys come around looking for when you want something for a particularly stringent environmental set of conditions like high temperature, corrosion, and so on. These are all stainlesses here, well, titanium, of course, is very corrosion resistant also. The MP35N and MP159 are made by SPS. They have the patent on the material, and they are super corrosion resistant and high strength up to about 220 KSI. Inconel X750 is used for high temperature, and the Haynes alloys, and then the A286 above 160 KSI strength is a special, because in order to get it above about 180 KSI, you have to work harden it in addition to heat treating it. Now, here's a table of fastener materials. I won't go through each one of these, but one of the things I just wanted to point out to you, and you'll have to go to this one over here on it, is how to figure out what the designation is. Now, the AI, SI, and SAE, usually the numbers are the same for the steel. And in this case, here we have the 2 is the class of materials from over here, which is a nickel steel in this case. The 3 is the approximate percentage of the main alloying element, which in this case is nickel. And then the 17 is the carbon content. So this is a low carbon alloy steel, 2317. That has no special significance other than the fact that it's used to just illustrate the system. Now, for the nickel chromium steels and molybdenum steels and so on, here are the ones that are used mostly for fasteners in alloy steels, the 4000 series. You have 4037, 4140, 4340, that type of thing that are used for the fastener steels. Now, on chemical compositions, I guess I better stay with this one over here for that also. Here you see the ordinary hardware store varieties, and you notice that all of these other elements are not listed. One of the things you can run into if you're having a real problem, sometimes you can get some of these steels that have things in them that you don't want. A guy was pointing this out to me from Lincoln Electric, that in welding they're running into that because a lot of steel is made out of scrap. So the scrap has most anything in it. So they're getting a lot of impurities that they don't want in it. And then you get down here the standard alloys, the stainless steels. One of the ones that I wanted to call to your attention on that is in the 300 series stainless steel down here. One of the ones that they left out here was the L designations, the low carbon, because a lot of the times you want to minimize the amount of carbon in it, so you use a 304L or 316L or something like that, and they did not put that one in that table, so you might want to just flag it. All right, moving on now to operating temperatures. Here I have grouped this in categories, and so the minus 65 and below, that's your cryogenic temperatures. Now, of course, those of you who have been around long enough remember the Atlas and Centaur. And, of course, they're liquid hydrogen fueled, so the temperatures you're running on that type of a vehicle are anywhere from about minus 300 to minus 423. So you cannot use carbon steels at those temperatures because they will crack like glass. Even some of the stainless steels won't go below about minus 150. Aluminum is good down to those temperatures. Then you go to the minus 65 to 450, which is an ordinary range for most engineering designs. Carbon steels are okay, and stainless steels are okay, but then you get into the business of needing corrosion protection for the carbon steel with the various types of plating like zinc or cadmium or phosphate or black oxide or whatever, and those will be covered, of course, later on in the platings and coatings section. Now, for the 450 and above, believe it or not, you can use unplated carbon steel up to about 700 degrees because the only thing you're looking at there is how much does the allowable drop on it for the temperature. So if you go in one of the books like Mill Handbook 5, you can find temperature curves for carbon steels, and you find it, use it. But you see, the reason I'm saying unplated is that an awful lot of the platings for steels burn up before you get to that temperature. So these are some of the ones that don't hurt you, at least. Now, and I'm just giving these because of their temperature range rather than the fact that you normally would not silver plate a carbon steel, but you do silver plate stainless steel. But silver, nickel, chromium plating, and chromium plating is used on some high-strength fasteners for aircraft landing gear, that type of thing. The black oxide coating that you're all familiar with from your hardware store bolts looks good and all that, but it burns off. Then you have diffused nickel cadmium, which is a special one that will be covered later. And then, of course, you can use the stainless steels and super alloys without anything. Now, we'll, although we have a corrosion section, I elected to put the, sorry about that. Here's the table of summary of fastener materials. And you can't read this one, so I'll go over to this one. One of the things that I wanted to point out to you here is that if you look at the useful design temperature on these, you find that A286 is one of the best, minus 423 to 1200. But you get down through all of these, and you find that this Haynes 230 at the bottom is the only one that will carry you up to 1800 degrees. Now, the significance of this is that we've gone through on the NASA program, the National Aerospace Plane, and developing all of these super duper materials to build airplanes out of, but we never did anything on developing fasteners to put them together because the regular metal fasteners is what the only thing they have to put them together. Okay, moving along now into the galvanic corrosion and stress corrosion area. Galvanic corrosion is something that we're all familiar with, although we may not use that title for it. If you get a scratch on the chromium plating on your car, it will rust faster than it would if it didn't have any plating on it, because you have a very small anode and a large cathode being the rest of the surface. So the anode is deposited on the cathode, which means that it rusts away. So rusting is a galvanic corrosion. And later on, we have a table on the galvanic series that will give you the location in the table of these, and the farther apart they are in the table, the bigger galvanic corrosion cell you develop between the two of them. And of course, cadmium and zinc are adjacent to aluminum in that table, which makes them compatible as coatings for steel fasteners used in aluminum. Then, and to further protect mating surfaces from galvanic corrosion, you particularly where you're putting in rivets, and you pilot drill one piece and then drill it through, you have raw surfaces that are not plated with anything. So you either use a zinc chromate paste, or there's a Mill 8802 sealer that will deter galvanic corrosion. Now here is the table of the galvanic series, and this is something you can find, I think Mark's Handbook and various places have it. And one of the things that I wanted to point out in this is that if you look at cadmium over here, see, it is right in the aluminums. Also, zinc is there. So if you use a cadmium plated fastener in aluminum, you will get less galvanic corrosion than you would, say, if you used a one of these down here, like a brass or copper or Inconel or something like that. Now, notice that there are two different designations for the stainless steel. They have active and passive. Normally, stainless steels are passivated, which they're treated with an acid dip to remove any kind of scale they had on them from processing, and to form a protective oxide on the surface. The passivation of steel corresponds to anodizing of aluminum. So that's why that they have it shown differently here, passive and active, because the passive is much less corrosion, or much more corrosion resistant. Okay, now going to stress corrosion. That is something that we're all familiar with, in a sense, but there's not much available in textbooks on it, because the study of it is a fairly recent thing. Now, stress corrosion, of course, occurs when a sensitive material is loaded in tension in a corrosive environment. Now, that sounds pretty easy. And what happens, the surface develops pits or cracks from exposure, and this, of course, gives you stress risers, which will cause the component to fail at as little as 20% of its calculated load capacity. Now, the thing about it, one of the reasons why I don't propose using the super high-strength alloy steel fasteners, if you can avoid it, is the higher the strength, the more sensitive it is to stress corrosion. So, you try to steer clear of using super high-strength fasteners in alloy steel for that reason. The stainless steels, most of them are not stress corrosion susceptible, other than the precipitation hardening 17.4 and 17.7. So you ought to look at that before you select the fasteners that you're going to use. Now here's another one that you can run into, although it's not a that common as decarburization. When you heat treat a carbon steel, you can actually precipitate carbon out on the surface. And I would compare this to like charred wood or something like that. You know, charred wood is how it's very soft on the surface, because this is essentially what you're getting. You're getting a heavy carbon coat in the outer surface, and of course it's not as strong as the parent material. And on machine parts, they sometimes just machine that off and go ahead and they can use the part. But of course on a fastener you can't do that, so you have to be careful about decarburization. And once again, it's on the strengths above 180 KSI. Now, temper brittleness is another thing you can run into on the high-strength fasteners. After you have quenched them, then you need to go back and temper them, which means holding them at a fairly low temperature to get the strength that you need. But that also causes the material to be brittle. So carbon steel fasteners above 190 KSI are a real risk as far as having brittle failure. Now you can use some of the super alloys at strengths higher than that, but not the ordinary carbon steel. Now going to carbide precipitation. This is something that gets people in trouble a lot, where they don't want a stainless steel to rust. And believe it or not, this is fairly recent, at least recent for me. Maybe for you guys it's ancient. But we ran into this on the Atlas and Centaur programs, in which we had joints rusting down at the Cape with this thing sitting on the pad. And this is stainless steel. It's not supposed to rust. But what they had on that, some of the sections were put together by fusion welding. And of course, the only way that you can prevent it from rusting on the 300, these were 301, is to solution treat it after welding, which means you take it up to about 1800 degrees or something like that and get the chromium back in solution. Because what happens, the carbon will combine with the chromium to form chromium carbide in the weld joint, and of course that pulls the chromium out. So if you had your regular 301 is a 18-8, 18 chromium 8 nickel, so you pull the chromium out. If it falls below about 12%, the steel rusts. So this is why that normally if you're going to have welded joints, you try to use a 300 series with a L designation, which is low carbon, and even use a low carbon weld rod. Or better yet, and this is what we did at Martin Marietta on the Titan, you use 321 stainless because it has titanium in it. Or you can use 347, which has columbium. And the titanium and columbium will combine with the carbon before the chromium will, so that'll leave the chromium in solution so that you still have the corrosion resistance. So keep that in mind when selecting fasteners for anything above about 800 degrees in the stainless steel, to use 321 or 347. Now, on material strengths, after the temperature and corrosion requirements have been determined, then you've got to look at the material strength. And once again, keep in mind that the higher the strength of the material, the more stringent the manufacturing and quality requirements become, because it's more sensitive to imperfections. If weight is not critical, it's better to use a lot of fasteners of lower strengths than to use a few high-strength fasteners. Use those old grade 8s if you can use them, and you don't have to worry about weight. Now here's metric fasteners, and that is one of the least understood, I think, between most design engineers. And I'll have to admit it's confusing to me, although my buddy Bing Glendoff, who came from Sweden, says that metric is the way of the world. He thinks it's great, but I still have trouble with it. So we'll go through some of the peculiarities of metric fasteners. On the property classes is the way that they specify the strength. and which is a tensile ultimate, and then yield as a percent of the ultimate in megapascals. And somewhere here, a megapascal is 145.04 psi for any of those who need to convert. Now, the material is not specified in the call-out, so you have to specify the material yourself, or otherwise you don't know what you're getting. So if you have like a property class 6.8, it's a carbon steel of some kind with an ultimate strength of 600 megapascals and a yield of 0.8 times that, because that's where the 0.8 comes from. Now, for some stainless steels, they don't use those rules, and so I have a table further down the line here that shows the peculiar type stainless steels, the way they're called out in the metric system. Now, here's something I had a little trouble with getting people to understand around here, because when we had a government decree to go to the metric fasteners for the CM1 project, or for all new projects, the metric aerospace fasteners are not available in the European market. They use American inch-pound fasteners on their airplanes, and I toured the Huck's rivet plant in Tucson a couple years ago, and the chief engineer told me at the time that the A300 people were their biggest customer at that time on fasteners, because there aren't any aerospace fasteners available in the European market. So you can get them in this country on special order, and due to the fact that the property class is not enough to define the fasteners, the NAS committee and our agency fastener committee came up with doing it this way. You put out these AIA, it's actually NAS specifications that are for metric fasteners only, and this is very similar to the MS or NAS sheets that you see all the time for the inch stuff, that you actually cover everything on there, the heat treat, the material, everything, and all the dimensions, coatings, and so on, so that you're completely covered. And you can also order metric fasteners from ANSI specifications. Now here's that kind of a square duck type table here for the stainless steel metric fasteners. And these different classes here, the A1, A2, A4, and so on, and then the 50, 70, 80, 45, 60, 50, 70, 80, and so on. For some reason or other, you need to add a 0 to those in order to get the actual strength of the material. They made them a class like that with that. So in other words, the 50 here is a 500 megapascal ultimate strength. And so the only way to identify them is to put them in a table like that where you can refer back to them. Now, the next table covers the different classes and the type of alloys that are normally used for them. The SE here is S, and SE is S is for sulfur, and SE is for selenium, that's normally added to the 300 series to make it more machinable. So presumably on this one, if you wanted to make your own and you wanted to cut them out of stainless steel, then you could use those materials. Here you have the 304L and the 321 and 347, which are the titanium columbium stabilized. And then here are the 400 series, which are only 12% chromium. And there's another table further over here that will show some of that. Now, going to the figure 2, I will not go through all of this stuff, but this is from the Metals Handbook. It just gives you a good overall view of the 300 series and the things that you do to it to tailor it to your needs. In fact, you probably can't read that even here at all, so it is in your handout, so you can go through it, and you can refer back to it at least when you're picking a material. The figure 3 shows the tailoring of the Martin-Siddick 400 series. And for those of you who always wonder what you should, what your scout knife is made out of, it's 440C, which is down there in the corner someplace. And that's the one that has the highest, except in the upper right-hand corner there, has the highest carbon and a lot of chromium, so that it will give you a high strength. You can go up to about a Rockwell 55 with it, C55, but it will nick a lot more readily. It's not as ductile as carbon steel. Figure 4 is, once again, this is the standard ferritic stainless steels of the 430 series, and the different ways of tailoring them, so I won't go through that. Then we go into a glossary of terms for materials, and once again, there's more here than I will cover in this presentation, but some of the things I wanted to call to your attention here about the alloy steels that normally we use the 4000 series. Then on aluminums, which I cover here, if you want more information on those, you can go to the Aluminum Handbook, which is put out by the Aluminum Association, and will give you more information there. If you look in the under aluminum alloys, the 2024 2000 series is heat treatable. The 3000 series isn't. The 5000 series is not heat treatable, but some of them are stress corrosion sensitive. And of course, the 6 and 7000 are we use all the time. They are heat treatable. The down there, the leaded steels, they're used sometimes, I guess, for making one-of-a-kind type screws. The lead, once again, is added to steel to make it easier to machine. Okay, going over to the next one there, the stainless steels. Once again, there's also a 200 series stainless steel that's very similar to the 300. And the other thing, we had a problem down at the Cape one time that they couldn't determine whether they had used 300 or 400 series fasteners. So the way you check is with a magnet. 400 series is magnetic, 300 series is not. Okay, moving on to the mechanical definitions part. You get into cold working. Plain carbon steels will cold work. Can you read that one over there or not? The plain carbon steels, you can cold work them during deformation. In fact, one of the reasons that they start out with the so-called wire, if you will, now wire, somehow 3/4 inch wire doesn't strike me as being wire, but that's what they call it in the fastener plants. They run it through, and before they run it through an annealing furnace to get it as soft as possible before they start. And so the fasteners are actually formed out of this annealed wire, and they are cold worked during the forming. In fact, I was involved in a court case on a product liability thing that the nut was actually harder than the bolt in this case, because the nut had been cold worked more than the bolt, and it stripped the threads off the bolt and caused a chair to fail, and the guy got hurt. So just wanted to point those out to you. Now, going on over to this next glossary of terms on the process definitions. On one of the things I wanted to point out there, killed steel is something that is defined here, which normally you don't find, and that is important because it makes the steel chemically stable so that you won't get into troubles on it. And I always point out defects that have happened along the line, and one of the things you remember, the cars, I believe it was the Fords and Lincolns that had the bumper beam that disintegrated on them. That was because the steel was not killed properly, as I understand it. And so you can get disastrous effects from it. The pickling is also a removal of oxide scale by dipping the steel in a bath. And these are important to have to prevent corrosion on the material during the manufacturing process, whether it be fasteners or general hardware. Now, the carburizing I covered, so we'll not go. Nitriding and case hardening, actually, in cases like that, it's where you have a material that you want it to remain ductile because it's some sort of an impact type thing. And so you case harden the surface of it by putting enough carbon on it that you can harden the surface just to get it slightly hard. Okay. Now, moving to platings and coatings, nearly all commercial fasteners are made of, since they're made of plain carbon or alloy carbon steel, you need some sort of a protection on them to keep them from rusting. So you can go from putting good old 10W30 oil on them down all the way to gold plating. Now, gold plating is not used on fasteners usually, but other than pins on tubes or something like that in the electrical field, electrical contacts and so on. But if something is small enough, gold plating does not become that expensive to coat it. But usually we go with something that is less expensive. So, but what you're looking for is a coating that will give you the protection at the lowest cost. So the other thing is with fasteners, you got to have a thin coating because the fastener threads have to be within tolerance after the coating, which is important. Now, I know that if you get nails or something like that, Ron Romanchuk drives nails all the time that have been galvanized, and that's a dipping process, but it's not used normally on threaded fasteners. Now, on temperature limitations, the coating is more likely to set the temperature limit than the fastener material itself. And some coatings can be a disaster when they decompose, like cadmium. You get hydrogen embrittlement from the decomposition of cadmium. And others, like the good old familiar black oxide, bake off without doing you any harm. Now, cadmium plating is, although people say that it is going away because of environmental problems, that's really not true. In fact, when I talked to a guy at Boeing about their development of replacements for cadmium, he said, as far as we're concerned, there is no replacement for cadmium. We're going to go ahead using it. So it's just the idea that you have to control the process in order to keep the EPA off your back. But it is used for electrodepositing alloy steel up to 190 KSI. If you get above 190 KSI, then you can't prevent hydrogen embrittlement, and you have to go to a vacuum deposit, which runs the cost way up. Now, here's something that is overlooked a lot and causes lots of problems. When parts are cadmium plated, they have to be baked within 2 hours after plating. And the reason I said 8 to 23 hours, it depends on who's baking them or if any baking is done, because I have heard of cases in which no baking at all was done to bake the hydrogen out. Whenever you do an electroplating process, it's done in some sort of an aqueous environment. So, as you know from charging your battery, you get free hydrogen whenever you put electrodes in water. So you have free hydrogen ions, and of course hydrogen can go where anything else can't go. So you get hydrogen given off during the process, so unless you bake the material right after it, you're in trouble. Now, cadmium melts at 610 degrees, so its service temperature is limited to 450. Now, the advantages of cadmium: it's good salt spray resistance, so it's very good in marine environment for airplanes where they're exposed to salt all the time in the winter time. It's consistent on the torque friction properties. It has a good galvanic corrosion location, and it doesn't decrease the base material fatigue strength. But the disadvantages: it generates cyanide during the plating process, which is nasty stuff that the EPA watches very closely. And of course, I mentioned the plating and baking has to be closely controlled to avoid hydrogen embrittlement. And it causes embrittlement of titanium. It's very expensive, and it has to be vacuum deposited on high-strength parts to avoid hydrogen embrittlement. So, but one of the other advantages of it that I didn't list there, it does not support fungus growth, whereas a lot of platings will. Since cadmium is kind of a toxic type thing, your molds and stuff like that in a marine environment can't grow on it. Now, zinc plating. Zinc is very common. Most of the fasteners that you buy that are plated are probably zinc plated. And of course, hot dip zinc plating is called galvanizing. You get roofing nails, that type of thing, are galvanized. The roof, the corrugated roof and so on, is galvanized. Now, the zinc plating doesn't generate the toxic byproducts that cadmium generates, and it's a lot cheaper than cadmium. But it will heal itself over by migrating over scratched areas. If you scratch an area, in fact, down at the Cape, they did a study on how far zinc would migrate, and it would go over a scratch about 1/8 of an inch wide and go back and heal. It will kind of heal itself to a certain extent. And it has a good galvanic location, but it's not as good as cadmium for corrosion resistance. And the torque tension friction characteristics, in other words, when you're torquing up a fastener, you can get such a variation in the coefficient of friction that you can get in real trouble on knowing what load you're putting on it. And but it can, here's one of the other bad things about it. It has a useful temperature limit of only about 250 degrees, so you can't use it at all where you have elevated temperatures. And it can cause hydrogen embrittlement, although it's not as serious a problem as it is with cadmium. Now, the phosphate coatings, this is used a lot in the automotive business because it's cheap. You throw a cup of phosphate in a barrel and put a bunch of fasteners in and shake them a few times, and you have phosphate-coated fasteners, more or less. And so the mildly protective layer of phosphate is formed on the surface, and there's 3 different ones. There's zinc, iron, and manganese, and the ones usually used for fasteners is the zinc or manganese. Now, the advantages of phosphate coatings: they're cheap. You can coat them with oil or wax to increase the corrosion resistance. And phosphate is a good primer for painting, so if you're going to paint something after you've phosphate coated it, that's great. And you don't get hydrogen embrittlement from it. But the disadvantage is not very good in corrosion. You get inconsistent torque tension friction properties, which means if you are supposed to torque a head bolt to exactly 2,000 pounds tensile load, you don't know what torque it'll take to do it if you have different fasteners that were at a different location in the barrel. And they have a limited temperature of 225 to 400 degrees. Now, nickel plating. Nickel, with or without a copper strike, is one of the oldest methods of preventing corrosion and improving the appearance of steel and brass, but it'll tarnish unless it's chromium plated. But it has a fairly high allowable temperature and good corrosion resistance. The disadvantage, it's more expensive than cadmium or zinc. It requires baking after plating to prevent hydrogen embrittlement, and it doesn't look too good when it starts tarnishing. Now, moving on to chromium plating. Chromium plating, of course, as you all know, is used for automotive and appliance decoration and very thin coats, but it can be used for fasteners. As I mentioned earlier, it's used for coating fasteners for landing gear, this type of thing, where you require the super high-strength fasteners or components, and so you can't use something else that would be like in a stainless steel, so you go to the very high-strength carbon steel, alloy steel, and then you chrome plate it. But you got to put, to get a good chrome plate, you got to put a copper strike on first, and then a nickel over that, and then the chromium goes over the two of them. Otherwise, the chromium is porous to a certain extent. So if you have, unless you have something under it to help it, it doesn't work out too well, or you have to go with a fairly thick coat. So, and it can be used up to about 1200 degrees, and of course it looks good. But the thing you run into, it's as expensive as stainless steel, so you only use it for the special cases. And it requires very stringent quality control, because you know what a disaster it would be if you get a hole through it and the salt gets in it. Then you have something rusting very fast. And of course you have to do the baking to prevent hydrogen embrittlement with it, same as you do with the cadmium plating. Now here's the ion vapor deposited aluminum plating. This is a special one that was developed, I believe, by McDonnell Douglas for coating of aircraft parts. And it was going to be used as an alternate to cadmium plating. Well, it doesn't give you hydrogen embrittlement, and it insulates to deter the galvanic corrosion, and can be used up to 925 degrees, and doesn't give off any toxic byproducts. But it's expensive and has to be done in a vacuum, so you can send it out to Joe Doak's plating outfit to get it done. And it's not as good as cadmium in a salt spray test, so it has not had that wide a usage that I know of. Diffused nickel cadmium is another one that was developed by the aerospace industry as a high temperature cadmium plating. And you put a nickel coating on first, and then put cadmium on over it, and bake it for 1 hour at 645 degrees. Now the advantage, you can get up to about 1,000 degrees exposure temperature, which is good, versus 450 for plain cadmium plating. But once again, it's expensive. You have to have extremely close process controls, and the nickel plate has to cover the fastener at all times to avoid cadmium damage to the fastener material. So, and it's not recommended for parts above 200 KSI strength. Okay, silver plating. Silver plating is used to prevent corrosion and as a solid lubricant for fasteners. For instance, it's customary to silver plate a stainless steel nut for a stainless steel bolt in order to prevent galling and serve as a lubricant. Now, silver plating can be used up to about 1,600 degrees, and its disadvantages, though, it's expensive, it tarnishes, and it shouldn't be used in direct contact with titanium. So its primary use in the aerospace field is just to coat stainless steel parts on stainless steel to prevent the thing from galling. Okay, we will take a break now, and resume with passivation and oxidation on the next session.